Previously, we talked about proving two triangles similar using angle-angle theorem and side-side-side similarity theorem. Today, we're going to talk about another one called side-angle-side similarity, which again is different than side-angle-side congruence. So instead of trying to construct these two triangles on this paper using the tablet, I have a sketch pad over here that shows this information. So I constructed AC to be 3 units long and AB to be 4 units long, and the angle A is 50. And then over here on the right side, I constructed side DF to be 44.5 units long, DE to be 6 units long, and angle D to be 60 degrees as well. So the same information here I have constructed here on the application. Now, something that we have to do now is show that third side. There's only one way to connect points C and B here, and only one way to connect points F and E. So when we draw in that third side, we can measure that. And now that we have that third side drawn in, we can measure the other two angles. So now that I have this information here, we can go fill in the stuff here on the table. So angle C and angle F were both 82 degrees. Angle B and angle E were both 48 degrees. AB, length AB and DE, we constructed those to be those lengths. So 4 and 6 units long. BC and EF, those sides were added after the construction. I had to connect points C and B and got that segment, and connected points E and F and got the length of that segment. So we have 3.1 and 4.6. And then the last ones, CA was 3 and FD was 4.5. So if these are similar, that means the angle should be the same, and we already have that. And the sides should be proportional or have the same ratio when we simplify it. Let's just start plugging things in. The ratio of the two angles, 82 over 82, that equals 1. That's a way to show that they're the same angle. You don't always have to do this. I just like to kind of verify that, okay, the angles are congruent. Now, when we look at the side lengths, AB was 4 and DE is 6. That can reduce down to 2/3. Or if we get the calculator out and get our decimal, 4 divided by 6 is 0.67. Then we do that for BC and EF, 3.1 over 4.6. Let's see what that equals. 3.1 divided by 4.6. That's 0.67 as well. It wasn't exactly the same as 0.66 repeated, but it's pretty close. And again, unless your construction is absolutely perfect, you're going to be off by a little bit here and there. And then the last one, CA was 3 over 4.5. And if we were to type that in the calculator, you'd also get 0.67. So yes, these two triangles, these two triangles are similar, and we know that because the corresponding angles are congruent, and corresponding sides are proportional. So all this information was derived just from given two sides that were proportional, and a congruent angle. So you can think about it as side, angle, side, side, angle, side. So based on just those three pieces of information, we know that these two triangles are similar. So here, if two corresponding sides of two triangles are proportional and their included angle is congruent, then the triangles are similar by side, angle, side similarity. Remember, included, when we talk about an included angle, that means it has to touch both sides that we're talking about. And we'll see some examples of that. So let's look at number 1 here. And first, we see that angle V and angle V are congruent. Those are vertical angles. And then we got to see if the side lengths are proportional. So I'm going to pair up these smaller sides. So 8 over 24. Does that equal, and I got to go in the same order, so smaller 14 over 49. Are those two the same ratio? Well, 8 over 24, that can be simplified to, if you divide the top and bottom by 4, you get 2 over 7. And in the red fraction, if you divide the top and bottom by 7, you also get 2 over 7. So when you reduce a fraction, you get the same thing. So these two triangles are similar by side, angle, side. We had side, side, angle, side, side, angle, side. The blue angle touches both sides that we're using in both of the triangles. So triangle VUT is similar to triangle. Okay, if we went VUT, we did VUT. We got to go in the same order. So VLM. And that is by side, angle, side similarity. VLM. The next one, we have a congruent angle that's 76 and 76 degrees. So then 9 is the smallest side here. 21 is the smallest side on the other triangle. 18 is the next smallest side, and 42 is the next smallest side. So I'm going to do 42 over 18 equals 21 over 9. Now you may say, well, you put the bigger number or smaller numbers on top in the first part of this example, and now you put the bigger numbers on top. Like I said before, it doesn't matter as long as you are consistent. I couldn't put my second fraction as 9 over 21 in this case. So if you were to reduce the left fraction, the 42 over 18, that would give you 7 over 3. Divide the top and bottom by 6. And then in the red fraction, if you divide the top and bottom by 3, you get 7 over 3 as well. So the two side legs, when you reduce the ratios, you get 7 over 3, so they're proportional, and 76 is our included angle. So these two triangles are congruent by side, angle, side similarity. So FGH means that we have to go in the same order. So triangle UVW by side, angle, side similarity. So this other example over here, again, we have vertical angles at U. And then we need to pair up the corresponding sides. Now, since both of these sides are 16, we should expect that if these triangles were similar, these two should be the same value, 39 and 48, but they're not. So we can kind of probably already tell that these aren't going to be similar, but you can always do the math just to make sure. 39 over 16, I'm taking these two. Does that equal 40 over 16? Well, obviously that can't be, because the denominator of both fractions is 16. So if these two fractions were going to be equal, the top should be the same as well. 39 is not 48, so these are not similar at all. And we're also going to talk about the triangle proportionality theorem. And basically, it's when you have a big triangle and then you have parallel lines, within that bigger triangle, you create smaller triangles, and there are some properties that occur when that happens. So if a line parallel to one side of a triangle intersects the other two sides, then divides the two sides proportionally. And then the converse is true as well. If a line divides two sides of a triangle proportionally, then the two sides, or then that's parallel to the third side. So basically what that looks like, and I'm going to erase some of these drawings, these outlines in a minute. So I have this big triangle here, and if I draw QS to ensure that it is parallel to UT, then the side lengths of the triangle are proportional. So I could use this 12 and 6 to get in conjunction with this 10 to get the length of QU right there. So let me erase this and show you what I mean. So since QS and UT are parallel, that means if I take RS, the ratio of that, and ST, that is going to equal RQ over QU. Okay, so now we can just plug in the values that we were given. RS is 12, so 12 over ST, which is 6. That equals RQ, which is 10. And QU, we don't know. So we can put X there. So that we can cross multiply, and we get 12X equals 60. We divide both sides by 12. X is equal to 5. So this length right here for QU is 5. In example 2, you may say, well, we're given all the side lengths. What are we going to do? Well, we're going to ensure that this is parallel, or determine if it's parallel. So if QT and RS are indeed parallel, that means 18 over 38 should equal 36 over TS, which is 80. Now, you could try to reduce both fractions, and that could work. You could try to reduce the left fraction and the right fraction. Another way to tell if these ratios are equal is you still by cross multiplying. If you cross multiply these, and we didn't do that up here, and we could have done that with all of these ratios. Instead of reducing the fractions, I could have cross multiplied and determined, did we get the same thing for both sides? Either way is perfectly acceptable. So if I do 18 times 80, I get 1,440. And does that equal 38 times 36? That gives us 1,368. Those are not the same. So then these two lines are not parallel. QT is not parallel to RS. If you were going to simplify these fractions, you would get 9 over 19 on the left and 9 over 20 on the right. But I know once you get to bigger numbers, it can be hard to simplify the fractions quickly. You may have to go down by 2s or 3s eventually to get the fraction in the simplified form. So you can cross multiply instead. Now in example number 3, we have 3 triangles here. We have this huge one. We have the smaller one, and then the smallest one. So we're going to be doing a lot of calculations here and labeling of things, so it could get messy pretty quickly. But we're trying to find X, Y, and Z. So I think we should find Z first, because we have 4 over 6, and that will equal 5 over Z. So I think that's the one we should do first. So when we do that, we'll cross multiply. We get 4Z equals 30. Divide both sides by 4. Z is equal to 7.5. Okay, so I'm going to write 7.5 here. Okay, so now we got to figure out what BE and CF are. So I'm going to draw a triangle ABE down here, very cleanly. ABE. We know AB is 4. We know AE is 5, and we don't know what BE is. That's X. Then I'm going to draw the whole triangle ADG. ADG, the whole triangle. And DG is 18. We can clearly see that. But we can figure out how long AD is. AD is this whole distance here. So 4 plus 6 plus 3, that will give us how long AD is, which is 13. So then we can set up our ratios to figure out what X is. So 4 over 13 is equal to X over 18. So then when we cross multiply that, we'll get 13x equals 72. So 72 divided by 13 is 5.5. We'll leave it at that. So X right here is 5.5. Okay. Then for Y, we have room down here. I'm going to draw the small triangle again. A, B, E. We know this is 5.5, 4, 5. Now I'm going to draw the middle-sized triangle. A, CF. Where we know that CF is what we're trying to figure out. And we can say that AC is going to be 4 plus 6, or 10. So we can set up another ratio. 4 over 10 is equal to 5.5 over Y. So then when we cross multiply, we get 4Y is equal to 55. And when we do 55 divided by 4, Y is equal to 13.75. So yeah, this problem had a lot to it, and you had to solve one part to get to the next part. We had to find X before we could get Why in this case? So drawing things out separately, I think, helps. You just got to remember to use the segment addition postulate, where if you add up parts of segments, you get the whole thing. So draw things out separately and label the information that's given to you. So thank you for watching. Make sure to pound that like button and subscribe.